this video, we're going to use the auxiliary equation to solve this differential equation. And in so doing, you'll see that once again we encounter complex roots. Now, if you watched our introductory video on the auxiliary equation, you know that the general form of the solution is y equals e to the mx. This can be multiplied by a constant, and m is a variable, obviously, but it corresponds to these differentials in the following way. Here we have 2 times the second order derivative, so here we would have m to the second power, and then we have plus 5. A first order differential, we have m to the first power plus 6 times, there is no differential here, that would be to the 0 power, that would be m to the 0 power, which is just 1. So this is the auxiliary equation, and we solve this to determine what m is, and then we'll have the solution to our differential equation. And again, we explain this in more detail in our introduction video, and we worked through several examples where we had distinct values for m from our quadratic equation, or we also had examples where we had repeated roots in our quadratic equation, and what type of solutions those gave us. Now, here in the past couple of videos, we've been dealing with a situation where we solve the quadratic equation and we get complex values for m. So let's go ahead and solve this. We will have m will equal minus 5 plus or minus the square root of that squared, which is 25, minus 4ac, that'd be 4 times 2, which is 8, times 6, which is 48, divided by 2 times 2 is 4. And then we can simplify this a little bit, and what we end up with is m equals minus 5 plus or minus I times square root of 23. And then in our introduction video concerning complex variables, we derived the relation that when we have a complex root for m, some real number plus or minus ib, that the solution to the differential equation then pretty much just follows right from that. It's going to have a cosine of b and a sine of b, each being multiplied by e to the ax. So here, for our problem, this is a, here's b. So once we know the relationship, then we could just simply write down the solution. Y will equal some constant C1, but let's back up. We wrote this down incorrectly. It's divided by 4, so we should have minus 5 over 4 and have this divided by 4. Okay, here's A and here's B, and here's the relation that we derived a couple videos ago, that here's a complex expression for m, then here is the solution to the differential equation. The power that e is raised to is always just the a term, and the cosine and the sine term come from the complex term. That's all there is to it. So here we would say y equals e to the minus 5 over 4 x times the cosine of the square root of 23 over, take that out there, over 4 times x plus c2 e to the minus 5 over 4x times the sine of the square root of 23 divided by 4 times x. And that is the solution to the equation. So again, once we realize this relation, then when we have situations where we have these complex roots, we can immediately write down the solution to the differential equation. And again, this relationship was derived in our video. I think it was titled Complex Roots, or Auxiliary Equation with Complex Roots Introduction, and we went into as to why this relationship is true. We actually derived it. Then once we realize this, we see what a useful tool it is. Now, this did not take very much time at all. Let's just consider one more example here. Suppose we have this kind of differential equation. Say we have d squared y x squared plus 4y equals 0. So the auxiliary equation is m squared plus 4 equals 0. M squared equals 4, so m equals plus or minus 2i. Now, we go back and look at our general relationship here. Here, a is 0, so this is just going to be c1 times the cosine of bx plus c2 times the sine of bx. In this case, b, of course, is just 2. So the solution to this equation is y equals some constant times the cosine of 2x plus a different constant, sine of 2x. And that's the solution. Here, of course, we didn't have any e to the ax term here because m is 0 plus or minus 2i. E to the 0, of course, is just 1. So that's the solution. And again, it's all predicated upon being familiar with this relationship, which we derived a couple of videos ago. Okay, that's it for this video then. A reminder that the playlist for all the videos is featured at the website digital-university.org.